Hello there, my name's Lloyd Alcorn and today I'll be proving Lagrange's identity.
The man, the myth, the legend, Joseph Louis Lagrange.
A very French name, but he was actually an 18th century mathematician and physicist from Italy. He made major contributions to calculus, mechanics, and number theory. His work still shapes how we understand motion, energy, and modern algebra today. So what's all the hype about? So I've seen Lagrange's name in my physics and linear algebra classes. This is really the reason why I decided to do this problem, so I could learn a little bit more about Lagrange's identity. So here's some applications, why it's even important. In geometry, it connects vector links and angles. It's basically explaining why perpendicular vectors don't affect each other's direction or magnitude. In linear algebra, it's the foundation of the Cauchy-Schwarz inequality, which is huge in data science and machine learning for measuring how similar two data sets or signals are. And then in physics, it helps describe how energy splits across different directions of motion. This is how a moving object's total energy can be broken down into its independent components. And then one really cool real-world use is in signal processing, things like cleaning up audio recordings or compressing videos. It's even used in voice recognition and noise-canceling headphones. It's basically deciding what's real and what's distortion. So overall, this identity can basically be said to be powering part of modern technology, which is kind of cool. So this is Lagrange's identity. And boy, does it look fun. Nah. Now, for real, this identity shows a deep relationship between two sets of numbers, or in geometry terms, between two vectors. And on the left-hand side, we have the sum of squared differences. This represents how different the two vectors are in each pair of components. It's kind of a measure of how independent or non-aligned they are. And then on the right-hand side, we have a more familiar expression. This combines the lengths of two vectors and their dot product. So what the identity is really saying is the difference energy between two vectors equals the product of their lengths squared minus the square of how much they point in the same direction. It's really a beautiful way to connect algebra with geometry. It shows how the structure of numbers reflects the geometry of space. So when looking at big equations like that, I think the first step that we need to do is just break it down into its components. So when breaking down Lagrange's identity, we took the right-hand side. So there were two components that had A and B, and we multiplied out the summations. So we're going to take a deeper look at both of these summations after they've been multiplied out. So I don't know if you noticed, but in the last slide I switched all the K's to I's. Personally, I like using I's better. It's the same algebraically. So we have this first expression, and it's still pretty tough to look at. So we're going to multiply it out algebraically. And in the book, it had a problem like this, and then it made an array. And it made an array of all the n by n terms. So we're going to break this down even further, and then we're going to see if we can spot any patterns. So if you take a look at this diagonal, this blue diagonal right here, very important, by the way. All these numbers are the same, right? So we got A1, B1, and here we got A2, B2, right? And then we got this lower triangle right here, this red, all the red. And all the A terms are going to be greater than the B terms. So we got A2, B1. Here we got AN, B1, where n is greater than 1. And here in this top corner, sorry, this top triangle, upper triangle, the B term is going to be greater than the A term. So we're going to come up with equations for each of these triangles, right? If we take a look at the lower triangle, we have the sum of all numbers where I is less than j, where your j term will be out front. So we got aj squared times bi squared. And then for our upper triangle, right, we have the sum of all numbers where I is less than j, where your first term will be your I term now. So we just switch it around, so it'll be ai squared times bj squared. Right, so right now we have equations for the upper and lower triangles. We're going to try to solve for this blue diagonal. Okay. So we got this blue diagonal, we're setting it equal to the original function, and then we're subtracting the two equations that we just derived. So here we're going to take our second component, and again we're going to multiply the summation out algebraically, and then create an array for the n times n terms. And if you see again, we got this blue diagonal going down. Very important, all these numbers are the same, right? So you don't have an I and a j, you just have an I, because they're all the same number. And then we have our upper and lower triangles, right? So if you take a look at the corners here, we got A1, B1, AN, BN, A1, B1, AN, BN. So they're the same. If you take a look here, we got A1, B1, A2, B2, A1, B1, A2, B2. So the upper and lower triangles algebraically are exactly the same, but they are rearranged different. So we're going to come up with equations for both of the triangles as you spell the patterns. So if you take the lower triangle, so for the sum of all numbers where I is less than j, you just have your j's out in front because 2 is greater than 1. So you got AJ, BJ times AI, BI. And then for our upper triangle, we're just switching the I and the J. So 2 is less than N, right? So you got AI, BI times AJ, BJ. So these two expressions, these two equations are algebraically the same, right? So if we're solving for this blue line, we take the original function and then we could just subtract 2 times the sum of all numbers where I is less than j, and then just take the components from these two, right? So we got an AI, a BI, and then an AJ, and a BJ. And if you take a look at this blue line here, right, you got A times A squared, and then you got B times B squared, and they're all the same, so you only need I, or I equals 1. That's where it starts. Interesting. Step 2, celebrate your successes in life. Sometimes you just gotta take a breath. The math hurts. It hurts my head explaining it. But now we're back. So as you could tell, the diagonals from both of the arrays were the same, right? So we could set the equations that we derived equal to each other. And then we're moving forward. And just when you thought it couldn't get any worse, it gets a little better. Right, so at first glance, this hurts to look at all these colors. What are we even looking at anymore? No, but for real, these are just the equations set equal to each other, and all we have to do is simplify algebraically. So we're going to take the sum of all numbers where I is less than j terms, right? This and this, and we're going to combine them, and we get this. And this could be factored, right? This is factored into AI bj minus aj bi squared, which is actually Lagrange's identity. So we rearrange, and this is the original identity that we had to prove. So it's proven. At least I think. Well, thank you. It's now 3:42 a.m. I can finally get some peace and rest. If I sound like I'm losing it, it's because I am. But that is life.